Hi, my name's Iain Duncan, and I am the author of Scheme for Macs, an open source Macs MSP external for scripting and live coding Macs with Scheme Lisp, specifically S7 Scheme from CCRMA by Bill Schottstaedt. In these videos, we've been looking at the new features in the version 0.2 release, and in this one, the final of the series, we're going to look at the scheduling and clock features that allow us to do real-time algorithmic composition in Scheme. Okay, let's get started. So over here I have a Max patch. This is an extension of the one we looked at in the transport video. So on the right here we have all the transport functions. I'm just going to start and stop that and clear them out. There we go. And on the left we have a patch for playing just a drum synthesizer through a VST instrument. It's not really necessary to understand what's going on here, but the important part is that it receives a message of note number, velocity, duration, and then plays a note. So if I click this, we're going to hear that. And I've got a couple hooked up so that we can change them. And we also have a receive from the Scheme for Macs object. And so if Scheme for Macs outputs a list message that matches this format, we're going to hear that note played. And I've hooked this up to a metronome so that we can check synchronization. This metronome is just banging the message, and just get it going. There we go. Okay. So let's take a look over at the scheme functions. So the first thing we're going to do is, well, let's make sure that our terminal listener is awake. There we go. Okay, the first thing we're going to do is define a play note function that takes arguments of duration, note, velocity, and sends them out, Scheme for Macs out 0. Okay, and now let's try that out. Okay, it's working. And you can see we also have the output of the message in the console, and that's because we're printing the output from Scheme for Macs up here. Now the delay functions expect a function as a callback that does not take any arguments. And so we're going to make one of those with the lambda function. We'll call it play44, and it simply wraps up play note 44 90 90. And let's try it out. Okay, that's working. So the first delay function is pretty straightforward. It takes an argument in milliseconds and a callback that receives no arguments. So you'll note we're just passing the name of the callback. There we go. And if you look in the terminal, you'll also see that the call to delay returns this gensim83. Gensim is a feature in S7, so it's a guaranteed unique symbol, and that's been returned because it's the handle for our delay callback. And we'll get to that more shortly. I've made a couple of convenience wrappers for delay so that you don't have to do this wrapping up in a lambda business. If we pass delay eval a list, which we can use the scheme quoting notation, we could just as easily use call to list. That gets wrapped up in a lambda function for us, and that will be what becomes our callback. There we go. And a second convenience wrapper is that if you call delay eval with a variable number of arguments, the wrapping into a list is done for you. So everything after the milliseconds is considered to be part of the list that we want to wrap up. And those exist so that it's easier to use these from messages that you make in actual Macs messages where creating syntax might be cumbersome. Another convenience helper to mention right now is there is a time function that allows you to see what Macs thinks the current time is. Okay, there's the current time in milliseconds. So if you wanted to do math on time, that's the function to use. Now getting back to the callbacks, the registration of the delay function returns the handle, the gensim. And if we save that handle, we can use that to cancel a registration in the scheduler. So in this case, I'm going to ask to play 44 in 3000 milliseconds, but then I'm going to cancel it before it plays. And there we go. So cancel delay takes the handle as an argument. Now the delay functions also have some siblings for working with Max's musical time notation, which are aware of the global transport. So they're affected by the tempo setting of the global transport. So for example, we have delay T, and we can use Max's rhythm notation. So I've quoted it because it's a symbol, like a string. Delay T 4N play 44. We delay 1/4, and we can also pass delay T an integer, in which case it's taken as ticks. And actually, I misspoke. That can very well be a float as well. Max uses ticks, but the ticks are not limited to integer values. Okay, put that back to 0. Now, an additional helper is DelayTQ. This one will quantize, but this is a little bit unusual. So DelayTQ takes two arguments, the delay amount and the quantize amount. However, what it actually does is calculate the quantization based on where the transport currently is. That means it doesn't care whether transport is running. And this is intentional because we want to make sure that if we create, say, a ringing delay and we stop the transport, our delay notes should still play. So DelayTQ is going to use, I'm going to ask for a half note delay, and I'm going to ask for it to be quantized to the nearest whole note, and it will figure out what that should be in milliseconds based on the current transport location and tempo, and then play it. So let's turn on the transport so you can hear that quantization synchronizing. Now I'm going to use this master start button that helps me keep our metronome here and the transport in perfect sync. I'll change the metronomes to the second sound, and we'll hear the quantization. So it's always starting on the top of the bar. Okay, those are the delay functions. Now we're going to take a look at the clock functions, and those allow us to set up things that are locked to whether the transport is playing as well. So the clock functions, there are 3 different clock functions. Right now there are just 3 global clocks. At a later date I plan to add the ability to add more clocks. But right now there's a millisecond clock, there's a millisecond tempo aware clock, and there's a tick clock. So the millisecond clock is going to set up a repeating function that it will call every 500 milliseconds. And again, it expects a function with no arguments. So every 500 milliseconds we're getting play note called through this lambda, and now we'll cancel it. Now millisecond t does the same thing, except that it's only going to play if the transport is running. So we don't hear anything, clock is registered. Now let's start the transport. Now if we stop this and we turn on this other metronome, we'll hear that as long as we synchronize the starts so that this one doesn't get out of phase with the master transport, these will be in sync. Oops, we are not in sync here. Hang on. Cancel any running clocks. Start it up. Okay, so we're staying in sync. Now, of course, we're only in sync because our tempo argument works in this case. We're sending 500 milliseconds, and we're at 120, so we're synchronized. However, we can use the ticks clock, in which case we can specify ticks, and we know we're going to stay in sync even if the tempo changes. So I'll make sure I canceled that one. We'll stop. We're going to put this clock in here, start it running. Now every 480 ticks, that's going to execute. If we change the tempo, they're going to stay they're going to stay synchronized. Now, there may be a lag of 1 tick as the tempo is recalculated for the next iteration. Sometimes you hear it, sometimes you don't. Okay, so that clock's locked in. When we're ready to stop, we can cancel the clock. Now, for the purpose of this demonstration, I made a max patcher master start and stop for my transports and my synchronized metronome, but we can do all of that in Scheme, and so that's what I've got here. I've made an example of a synchronizing start function. So it calls transport seek, sets it to 0, registers the clock at 480 ticks. Oh, something I forgot to mention, the clock ticks clock has a different argument signature than the other clocks in that it expects to take ticks as the first argument. And so your clock tick handler can directly look at what tick you are on more easily. So in this case, we've declared a lambda that takes the ticks function and then ignores it. But we could just as easily do something. So we could have this clock registered, say, every tick, and modulo 480 it might play. Okay, back to the start function. So this is a start function, and it's got a few responsibilities. It sets the transport to 0. It registers our clock at 480 ticks. It then starts rolling the transport, and it also starts the metronome by sending a message to the metronome. So what I've done is I've given this toggle a scripting name. I've called it metro start in the inspector, and when I call send metro start 1, that gets flicked on. So let's define that function and start it running. Everything is synchronized. So I similarly made a stop function. It sets the transport state to not running, sends the metro the 0 signal, and cancels our clock. Okay, we're stopped. Now, the clock is one way of making a repeating chimer, but another way of making a repeating chimer that's potentially a great complement and sometimes more interesting is to have your delay functions schedule their next repetition. And this is sometimes called in algorithmic composition circles temporal recursion or self-scheduling delay. So let's take a look at that. I'm going to make a function. I've called it play recursive, and it plays the note, and then it calls itself again. So we have DelayTQ. It says quantize to the quarter on the next quarter, call play recursive once more. Now, one gotcha for these self-scheduling functions is sometimes it can be hard to cancel them. So there are a few strategies for doing this. One of them is you can have some kind of a conditional around the recursive call. So you could have a global variable for whether this process is playing and set it to false at the top, and then it won't schedule the next iteration. Another option, and the one I've illustrated here, is we can save the handle for that delay to a variable that is out of scope of the function, so we can access it from outside. And so what we're doing here is we're setting handle 1 to the callback handle for our recursive delay. So I'm going to put all these in the interpreter, and then we're going to kick off the process. Okay. And I'm going to cancel it. Now, let's, I think that might have been running 2 clocks. Okay. That sounded like it was 8th notes. Ah, yes, there we go. We had 2 clocks running. So now we've got the quarters. Okay, let's try that again with only 1 clock. So there's an example of the gotchas. it's a good idea to make sure you clean up your clocks and cancel them. And if you do get stuck, of course, you can always just reset the scheme interpreter. That's going to wipe out any clock definitions, and you'll start fresh again, but you will need to reload all your code. Okay, so let's try that one more time, see if we can do this without a mistake. That sounds better. And I will cancel it. And now I want to demonstrate one final thing, and that's that these self-scheduling processes, because they're quantized and they're running off the master scheduler, they will stay locked in with anything else happening on the transport. So I'm going to clear and stop the transport, and this time I'm going to turn the metronome on, and I'm going to start the recursive delay and then start playing, and we'll see, well actually we'll start playing first. Okay. And now we're quantized to the quarter, so when I evaluate this, our process should kick off and its first start time should be quantized to the quarter. There we go. And in this example, if we change the tempo really fast, you will hear that there will be one click that's out of sync as the quantized time may have been calculated before the change of tempo. Yeah, you could hear one click as it chased. So that really only shows up if you change the tempo quite dramatically, and you could certainly program around it as well. And now we'll cancel. Okay, so that's a brief overview of the new scheduling and clock functionality, and I've tested it pretty thoroughly. I'm sure there are still some issues lurking that we will find together. The scheduler code is quite complicated, but it does stay locked in and it does perform under high loads and high tempos, and I think it's going to make a lot of things, interesting things possible with Scheme for Macs. And if you play with these and make some progress or have suggestions or find bugs, I would love to hear about it on the mailing list or on the GitHub site as issues. Thanks very much.